All right, so pre-lecture for day 4, dealing with forces. So forces are vectors, so everything we dealt with last class dealing with vectors is going to apply here as well. And statics is also based on forces and based on Newton's 3 laws. And so we saw these previously as well on day 2. So just go over them briefly again. So first law, any object at rest will stay at rest unless there's a force acting on it or an unbalanced set of forces acting on it. So that's something that for statics is very important because we always have things that are sitting at rest. That's the point of this class. We don't care about the moving part of this. So if anything is sitting there, not moving, it's going to stay not moving unless there's an unbalanced set of forces acting on it. So that'll be important for us. Related to that is the second law. This is the standard force equals mass times acceleration. Again, here looking at statics class, statics, things are not moving. If they're not moving, they're also not accelerating. So acceleration is 0. So the equation we're going to be dealing with a lot in this class is that the force, the net force, is equal to 0. So sum of all forces equals 0 is an equation you'll be writing down a lot in this class. And then third law, equal and opposite forces. So again, if I go and push on this wall back here, it's going to push back against me with that same amount of force that I'm pushing against the wall. So that's also going to be useful for us when we talk about things like reaction forces. And if I have a ladder that's sitting on the ground, there's a reaction force holding the ladder up. There's a reaction force when the ladder is tilted against the wall. So again, something we'll be dealing with quite a bit in this class. So as I mentioned, forces are vectors. So everything we've dealt with last class is going to apply here as well. But there's 2 main types of forces, and the distinction is actually very important because Newton's second law that we just saw, sum of all forces equals mass times acceleration. Those forces are specifically the external forces, so forces from the outside pushing in on that object. There's also internal forces that can be developed inside an object. So again, if I come along and I push on this wall, me pushing on this wall is an external force on the wall. I'm external to the wall, pushing on it. But as I push on it, internal forces get developed inside that wall. So you can't actually see it because it's a really, really small effect. I can't see it either. It's not the fact that you're far away, you can't see it. It's the fact that when I push against this wall, I'm actually slightly deforming it. So when I push on the wall, it actually goes inward a very, very small amount. And that internal deformation causes these internal forces. And those internal forces are things that are going to be very important in one of your next classes, Mechanics of Materials, CE 220. And the way to find those internal forces is to look at the external forces, which is what this class is about. So again, here, what we really care about and what we only care about in this class is the external forces acting on an object. Actually, near the end of this course, in weeks 8 or 9, way at the end, we'll actually start to look at some internal forces that get developed, but those all depend on the external forces. So we really want to be looking at only the external forces that are occurring. Because again, those are the only things that actually go into Newton's second law. One thing we can do with forces is look at their line of action. So the line of action is essentially the direction in which that force is acting and also going through the point of application. So I have some force down here being applied at some angle to this object at this point, and draw a line through that point at that same angle. That's the line of action. And what I can do with that is, even though this force technically is pushing up to the right on the bottom of this object, it's completely equivalent to moving it anywhere along its line of action. So more concrete example here, I have a force at the bottom of this little box pushing up. I can move that force to the middle and pull from the middle in the upwards direction, or I can attach it at the top and pull up. And as long as these forces, this value in terms of magnitude, how much force is actually being applied. As long as that number is the same, all three scenarios will have the exact same effect on this block. So it doesn't matter whether I push it from the back, whether I pull it from the top, whether I pull it from the middle, or push it from the middle even. It doesn't matter. All those are completely equivalent in terms of what this force is going to do to that block. So forces, I can move along its line of action. That's called the principle of transmissibility. So it doesn't matter where this force is actually acting, as long as it's somewhere along its line of action, it'll have the same effect. And so there's a few common forces that we're going to deal with a lot in this class. The biggest one being gravity. So a lot of times in statics class, you're building things like bridges, buildings, things of that nature, and you want your bridges and buildings to not fall down. The thing that's going to make them fall down is gravity. And so gravity is an important force to deal with. So gravity, also weight of the object, same thing as the gravitational force. That weight is just mass times g, so g being either 9.81 or 32.2, depending on whether we're in SI or US units. And then just the mass of the object times that value gives us its weight. The weight always officially goes towards the center of the Earth. For our purposes, we're going to call that down because we usually deal with small enough objects that just the center of the Earth is down from us. So weight generally goes down. And in terms of its point of application, where on the object we can place that, if the object's homogeneous, so there's no significant changes in the density throughout the object, then the weight pretty much goes right in the middle, the geometric center. And so a lot of times if you're dealing with the weight of an object, you find what that value of the weight is, m times g, and then in terms of where to put it, right in the middle, and then pointing down. And that is our gravitational force or weight force acting on the object. In the very rare case where the object's not homogeneous, we don't really deal with that too often in this class, but if you do see a problem like that, then the weight just has to go at the center of mass, which may not be the actual geometric center, but the weight's always placed at the center of mass. And we'll kind of talk about that a little bit later, a few weeks from now. Another type of force we deal with a lot are cables or ropes or wires. So a cable or rope or wire can pull on an object. It can't push on an object. So anytime you have a cable attached, there's some force, usually called T for tension. So some tension force. Tension again means you're pulling on it and not pushing on it. So I have some tensile force T pulling on my object at whatever point it is located. And the other thing about ropes, cables, is that this tension force acts in the same direction as the rope. So this cable pointing down to the right in this direction, the tension force acts along that same line. So whatever direction the cable's going in, that's the direction my tension force is going when it acts on this pole. Another thing about that is this is generally the way you set it up. So you put it where it's attached, draw it along the wire. But again, due to the principle of transmissibility, I can actually put this tension force anywhere I want. So this tension force up here is the same thing as the tension force down there. Again, pulling on this object. The other thing about ropes is that due to that principle of transmissibility, the tension force anywhere inside the rope is the same. So if I want to, instead of looking at this pole, I have some tension force pulling down on this pole in this direction. If I want to look at what this rope is doing to the ground, then the tension force down here in the ground is exactly the same as this tension force up here, because again, the tension has to be the same everywhere inside the rope. So this brings us to pulleys. So again, the tension force being the same everywhere inside a rope. If I string that rope over a pulley, then the two tension forces in that same rope are going to be the same. So these two tension forces, T2, are both equal because again, the tension force has to be the same everywhere throughout the rope. Now that has one huge assumption associated with it, and that big assumption in this case is that this pulley is frictionless. So if this pulley is frictionless, there is no other force, and that's what makes these two tension forces the same. If this pulley had some friction involved, then these two tension forces might not necessarily be the same because there would be some friction involved, and you have to pull on one harder than the other to make this thing move. So again, for purposes of this class, we're going to assume that any pulley you see is frictionless so that the two tension forces can be treated to be equal, as in this case. So another type of force we see a lot are reaction forces. So the simplest version of a reaction force is a normal force. So again, if I go along and push against this wall here, the wall pushes back against me. That's Newton's third law, equal and opposite forces. That reaction force pushing back against me is this reaction force. So that equal and opposite force at the wall pushing back against me are these what we call reaction forces. A lot of times they're denoted by N for a normal force because that force is perpendicular to the wall. So I come along, I push this wall, I'm pushing perpendicularly against it. So it's going to push back perpendicularly against me. And so anytime that's the case, I have a normal force called N. And so that's what would happen here. If I have this ladder, I have this ladder sitting against the ground. There's a reaction force or a normal force pushing back up against the ladder to stop it from moving through the ground. It's also leaned up against the wall. So there's a reaction force or normal force from the wall pushing it and stopping it from moving through the wall, essentially. So reaction forces and normal forces they come from the same thing. Normal forces are specifically ones that are normal to the surface. So again, these two guys here, Rx and Ry, they would be normal forces. There are certain scenarios where you could have a reaction force that's not normal to the surface, in which case that would just be a reaction force. It wouldn't be a normal force, but they come from the same thing. They come from basically stopping objects from moving through solid walls, solid floors. And then related to normal forces are frictional forces. So any rough surface is going to have some friction involved with it. So rough surface by definition has friction. A smooth surface by definition does not have friction. So anytime I have a rough surface, there will be friction forces as well. The frictional force is related to the normal force. So the magnitude anyway of the frictional force is the coefficient of friction denoted by mu times the magnitude of the normal force. So for example, this frictional force down on the floor, FF1, will be mu, whatever the coefficient of friction between the ladder and the floor, times this normal force Ry. That would give me the magnitude of this frictional force FF1. Similarly, FF2, whatever the coefficient of friction between the ladder and the wall, times this normal force Rx. That would give me the magnitude of FF2. So mu, my coefficient of friction, there's actually two versions of it. There's a static version. So if this ladder is not moving, then there's a static value for the coefficient of friction that would give me this frictional force FF1 and FF2. However, there's also a kinetic version of the coefficient of friction. So if this ladder is sliding, there's then a different value for mu, which then is also going to give me a different value for FF1 and FF2 because I have a different value of mu. Basically, if you ever tried to slide something along the ground, if it's not moving, it takes a lot of effort to get it to move. And then once it's moving, it actually takes less effort. So the amount of pull you have to provide is less once it's moving. So the kinetic value of the coefficient of friction is generally about 20% less than the static value. Again, for our case in this class, we're generally dealing with statics, so we're dealing with things that are not moving. So we'll be dealing with the static version quite a bit. The dynamic version comes into play in dynamics class. I believe that's ME 230. And then the last thing about friction is that it always acts against the motion or against the possible motion. So if it's already sliding, friction acts against whichever way it's sliding. If it is not sliding yet, it's a little bit more tricky because sometimes you don't know exactly which way it's going to slide. Sometimes you do. For example, this ladder, if it is going to slide, this bottom is going to kick out to the left, meaning my frictional force FF1 has to act to the right. And if that kicks out to the left, the ladder is going to come down. If the ladder comes down, it means my frictional force is going to act up. So in this case, it's obvious which way the frictional forces will be acting. Some cases we'll see later, it's not. And the last force we see quite a bit in this class is a spring force. So anytime a spring is compressed or extended or stretched, it's going to have a what's called a linear restoring force. So basically, if I stretch my spring, it's going to want to pull me back in to get back to its unstretched length. If I push on it, it's going to want to pull me, or it's going to push back against me, back out in the same direction, again, to get back to its unstretched length. And so that magnitude of that spring force, Fs, is the spring constant, K, times this displacement x minus x0. So x minus x0, x0 being its relaxed length. So x minus x0 is essentially how much you stretch it or compress it. That value times some spring constant K gives you that spring force. And so the constant K really depends on the spring. You could have some really small springs that are easy to compress or stretch. And so in that case, you have a small value of K. Or you can have really big, huge springs used in like big diesel trucks and things that are really, really hard to stretch or compress. And so those will have really big values of K. And so the K basically depends on the spring, how strong it is, how stiff it is. The stiffer the spring, the larger the value of K. And then the last thing here is that there's this minus sign. Minus sign essentially means it's against the displacement. So I have some displacement, x minus x0. Minus sign means that my spring force acts in the opposite direction. So here's my unstretched spring, some length x0. I then go and displace it. And so Fs is a bit misleading here. This Fs is actually me pushing on the spring, and the spring force actually is the equal and opposite force. So this Fs is the force from the spring on me. So it's actually the equal and opposite version of this guy, but I need to compress the spring. So I push on it. This spring's going to act against me. And again, that's where this minus sign comes from. So this minus sign really just means direction. So you don't necessarily need to write it down all the time. It's just a matter of, does it go to the left or to the right? So in this case, if I'm looking at this spring, again, if I'm pushing on the spring to the right, it's going to push back against me to the left. And in that case, it'll be push me to the left. So those are the main types of forces we'll be seeing in this class. So during class today, we'll go over some examples of these forces. So we'll have some weight forces, some spring forces, some normal forces, and we're generally going to be putting them all into Newton's second law. So sum of forces equals 0. And that kind of leads us into the next day's class as well, which is particle equilibrium. So I'll see you later today or whenever next class is for you. And we'll see those examples.